I'm going to embark on a new set of new channel here. So I'm going to start on covering review of Physics 1 and Physics 2 with lots of problems. Today is our first session, and I hope to keep it simple and straightforward. So this is not the place you're going to learn this for the first time, but if you have some questions, some conceptual difficulties, you can come back to this and probably clarify what are the main ideas. Okay, so let's start with just mechanics part. So this part is called kinematics. Kinematics, like study of just motion, how you describe motion, things like that. So here is, say, some point particle, a point object is moving along this path. So this path is what is called trajectory. So this is trajectory. Okay, and so at some time it's over here, and it's a little bit later because the path is pointed, right? It got the direction is going in. So it's over here, and it's a three-dimensional, maybe like a fly is flying around in the room, and this is the room. So describe this motion. You can just draw it out on a piece of paper, and you can tell people. And you want to go a little bit more than that. You got to draw a little bit. Maybe you want to become analytical, handle this more quantitatively. Then you would need some kind of reference. So here is a reference point, origin. So that's the reference point. And these are some reference directions randomly you picked up. Maybe this is like a east facing wall or something like that. Maybe this is east and this is up, and maybe this is north, this is south. So but the upshot is you need this three coordinate system, and you need a scale. So you need coordinates, and you need some scale, like, okay, you have to mark the coordinate system. So that's the scale. So you need reference, direction, plus a scale, and that's what we call coordinates. And here I'm using Cartesian coordinate. It doesn't have to be Cartesian coordinate, but it has to be coordinates. So you can have a polar coordinates if you're in 2 dimension. You can have in the 3 dimension. You can have a spherical coordinate, a cylindrical coordinate. There are many other coordinate systems that are suitable for certain problems for certain symmetries. You want to exploit the geometry of the problem, so you can use coordinate system accordingly. But here, to suit our need, Cartesian is the most commonly used coordinate system. Okay, so in here, so there's a point P at that time. Over here, redrawn it over here, just point P, and it's got coordinate x, y, z, and I'm drawn a little bit non-traditionally because I'm going to use x and y like that in the future, and then z will become this way. And how do I know which way z is? Well, let me come back to it, and I'm going to check something and then come back. Okay, this point P is at time t. So this point P at time t is called where it is. So this is position. So position, say at some instant t. So it's instant by instant, and usually you'll draw an arrow from the reference point to that, and that arrow will used as a what is called vector. So this arrow will be you will do like this, sometimes you're going to write it like, we're going to write like this. Some other time I'm going to write some other time I'm going to write like in a notation, and some other time I'm going to write this is a collection of 3 coordinates over here like x, y, and z. So I'm going to write x, y, z, and sometimes you're going to write this x as a function of t, y is a function of t, and z is a function of t. And some other time I'm going to pick like this direction will be I hat, unit vector, 1 magnitude. This will be j hat, and thing parallel to this will be k hat. So these are the unit vectors of magnitude 1 and direction along those guys. So sometimes you can write in vector notation will be x I hat plus y j hat plus z k hat, or sometimes give specifically what is the independent variable here. So that's the position. And over here you see I wrote position at point when it was at P. So sometimes we're going to be able to write RP instead of R at T. So these are all different ways of writing the same thing. Okay. Now displacement is displacement between 2 instants of time. So displacement is a change in position between, say, instant t and instant some other time, which I'm calling t plus so maybe t1 is t, or t equals to t1. Let's call it instant here is t. Sometimes we're going to between the first one I'm going to sometimes call t initial, sometimes called t1. So all these names will be used for the initial point, and the final point will be instant t final, t2. These are all the names we're going to use. Or sometimes going to just say just whatever t2 is away from t1, and delta t. The notation you should know, delta t. So this is read as delta, this symbol t. This symbol delta means 2 context dependent use. Okay, like it will mean delta t may mean a small amount of whatever this thing is of that stuff. It may also mean change in that stuff. So there are 2 meanings when you look at that, and you have to have what is the context. So here we're just meaning a small amount of time later is at Q. All right. So position clearly change from P to Q over this time. Even if it doesn't change, displacement will be 0. Okay. But if it did change, then we will draw an arrow from P to Q, and that vector we'll call displacement. So P to Q, that's the displacement. So that's one way to write displacement. Let erase that when we will take care of it. So P to Q. That's another way to write is R P to Q. Another way to write is delta P. Delta R vector P to Q. Another way to write is just delta R. Okay, so this represents this arrow, basically arrow from P to Q. So vector arrow P to Q also represents the displacement, and there are all these other ways. So now these are all kind of abstract, pictorial, not very useful for making calculations, but it's very good for thinking, conceptualizing. So if you look at this, Q, its coordinate will be a little bit different than X, so which is going to call delta X, a little more, it's X and something I'm going to call delta X. This is not change in X, it's just delta X, a small amount of X added to X or subtracted to X, something like that. So this is, I could have called it, this whole thing could be X for Q, Y for Q, and Z for Q, just like this is X for P, X for Q, or Z for Q. So if you look at this arrow, which is displacement, and you bring it over here, the coordinate of this thing will be just delta X, delta Y, delta Z. So like if you you bring this to the origin, so you bring the origin over here, then the Q will be how far away? It will be just this kind of way. So this will be like a vector which can be, of course, moved around. So this is actually a true vector. You can move this vector over here. As long as you can maintain this and size same, it has same vector. So the vector can move around in space. They will maintain. If you look at what's the difference between this guy and this guy's X and Y will be just delta X, delta Z. So another way to represent this vector is go delta X along the X, do delta Y along the Y, do delta Z along the Y. And how did I get that? This another is X of Q minus X of P, Y at Q minus Y at P, Z of Q minus Z at P. And of course this is a vector, so another way to write this stuff is delta X I hat, delta Y J hat, but delta Z K hat. I know this is really very basic stuff. Most of you should already know this stuff. We're just reviewing it for completeness of this new thing when I'm started to do. I'm going to do problems in the future, but today we just conceptual things we're going to do. And we have to do first foundation. So we want to talk about speed now. So what's a speed? And then we're going to have velocity and acceleration, okay? So let's talk about speed here. Speed is actually the distance you are covering along the path, okay? So it's actually rate at which you are covering distance along the path. Okay, so what does this mean? So say the path is like that, and here is a P, here is a Q. So here, so you would put let me actually erase this and draw a little bit like this. So here is P, here is a Q, okay? So there will be like average speed between P and Q. So there will be average speed. Let me erase this because it's going to be, let's erase this out. So if I have this, and this is at some time t, and this is at time t plus some delta t, okay? And this So you went like that, and I want to know what the average speed there is. So you know what the ruler here is, right? The ruler is, those are 1 meter, 1 meter ruler. So I'll go and put this 1 meter ruler. So I'm going to use a scale to mark the path, which is trajectory. I can say ink here. So is there 1, 2, 3, 4, 5? Maybe if this was 0, then you went to Q is 5.5 maybe. And maybe the time here is T equals to 5 seconds, and maybe T here is 7 seconds. That means delta T is 2 seconds, right? Because if this is T plus delta T, then time here is 5 seconds, so this is 2 seconds later than this time, right? Okay, so average speed will be how much distance on the trajectory you covered. So you got 5.5 meter you covered on the trajectory, divided by, it took you 2 seconds. So this average speed, we can call it average speed, and no arrow or anything, because it's really directions is changing. There's no arrow for the speed. Okay, so it's just a, we call it, it's a scalar quantity. Hopefully this is correct. Okay, I think this should be 2.7. Let me see. And this should be, what is it? So 2, I have to go back to really, yeah, 2.75, 2.7. I have to have 2.75. 2.75, that's correct. Okay. So this is going to be the speed. Kind of hilarious, right? Talking such an advanced concept, and then I'm going back to the grade school. All right, going back to it. So this is just one number. Even this thing happening in 3 dimension. This is happening in 3 dimension, but speed is just one number because it's along the path. Any point taking a path, just one path. So this is average speed. But let's see, you wanted to make a, maybe not 2 seconds later, maybe over here it's going faster than over here. Then you want to be a speed close to T. So you want to know what time it was in this, maybe this 1 meter, what time it took to cover. Maybe it's took T at that point is only 5.1 second. Okay, then if you just if you look at this P to say R, compare that, is going to give you what's happening around there. So near P, in this particular example, V between P and R, P to R, P to R, P to R, that should be, it went 1 meter, but it was 0.1 second. So this is 10 meter per second. Maybe it's over here it got slowed down, and this last half a meter it covered, took a long time to cover. Maybe at this point t was not 7 seconds but 6 seconds. So it covered 0.5 meter but took 1 whole second. So this maybe it was, this will be 0.5 meter per second. So you can see that, you know, it's fast, slow, but at different places. So there is a concept called instantaneous speed. So suppose I cover this this distance that's being covered, let's call it distance covered in time, dt. I'm going to now, or maybe delta t, I'm going to say delta t, b delta s, use the new symbol s. Then I can say take a limit delta t goes to 0. So this will be a calculus concept. So we're looking at the distance covered from, you know, some point along the path. So I mean, wherever you want, we start to have this s equal to 0, and then you keep counting s bigger and bigger s. So the p doesn't have to be set at 0 anymore. You just, it is, this whole trajectory is defined to be a function of time. So s as a function of time, this will be a speed at instant t, and so we can call it v at instant t. Of course, in 3 dimension, you can, you know, choose a parameter to parameterize the path. So this path can be parameterized. It's like you could say, well, from here to here, that was the time of interest. You can say x of t, y of t, and z of t. This is the path, and t goes from some ti to t final. So that is the path, and you can plot it, right, in 3 dimension, and it will look like something like that. All right, so this is the path. Then what is the speed? Well, the speed will be, we will take a derivative of these guys. ds dt will be a square root of dx dt square plus dy dt square plus dz dt square. So that will be ds dt. And one way to say this will be the case is, if you look at from the path, so an incremental distance from, so if you look at t to t plus dt, all you have to have these guys all, so at this will mean x plus dx, y plus dy, z plus dz. So the distance, so if I go between here to here, and this is dx dy, just in 2 dimension, this will be ds. So in 2 dimension, in 2D example, ds will simply be square root of dx square plus dy square. So if I divide ds over dt, so square root of dx square plus dy square over dt. So I can actually take this inside, right? So this will square root of dx square over dt square plus dy square over dt square. But this kind of thing is just a formal. What this means is dx over dt square plus dy over dt square. This is this is one way to think about it. If you're comfortable with that, no problem. You don't. If you're not comfortable, that's okay too. Right now, it's not very important for us. But the idea that speed would be along the path is the most important thing. Okay. For instance, suppose here is an example. You went all the way. So here is a P, and you came back to Q, and then you keep going. Okay. So maybe you're some closed loop, you're going around and around. Okay. Well, what's the average speed? So what's the average speed between P to Q? Well, direct distance is nothing. You have to go, this is the path you took. You put a ruler and figure out how much distance have you gone to get to Q. So if suppose you went to twice, then you're going to do it twice the distance you've gone and twice the time, right? So how much, suppose you went around to get to the same place, starting place, but you went around 3 times around. And the one time around distance, time is say 5 seconds. Went around in 5 seconds. Let's use 10 seconds so you have an easier calculator. So 10 seconds. And once around, distance is say 20 meters. Okay, once around distance 20 meters, and you went around 3 times, and it took you 10 seconds. So the total distance you went is 3 times 20 meters, and total time it took you is 10 seconds. This is the time for going around 3 times, and that's the 3 times distance. So this will be 6 meters per second. So this is the actual path you took. So this is the speed, okay? But it turns out speed is very important when you're looking at energy. We're going to do kinetic energy later. In between, what we're going to do is lots of things with vectors. This is not a vector, so this is just one number, and that's why it's very, 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 very important to know speed. And speed, this one number, because it's only one number, and it's called scalar. It is not a vector. So wherever a problem can be done just by speed, you do not go the vector. Okay, let's go back now. So we've done the speed. The velocity is actually just straight from what we are talking about, displacement. So displacement was this, right? How much you went in the x direction, how much you went in the y direction, how much you went in the z direction. Or in vector wise, you're going to write like this. And this whole thing happened in time. This happened in time. In time duration, it took you is t to t plus delta t. So that's how much it took you, took delta amount of time. So the ratio of these two gives the average velocity. So let's take another place and take another ink. So displacement over time taken, this is called average velocity. And this is a vector because displacement is a vector. So there are many ways to write it. One is this, and we can write x delta x this much along the x direction, this much along the y direction, and this one is z direction over delta t. So you can write down delta x. Oh, so this is the rate at which x coordinate was changing, and this is the rate at which y coordinate was changing. This is the rate. So this basically is a collection of rates of each coordinate of the object with time. So this part is x changing, this part is y changing, this is g changing. So another way to write is v average, and this is the x part. So this is not a vector, this is just a number, one number, not a vector, because I need to have a vector and have a collection. V average, the y part is changing, v average z part is changing. So these are the names of these things. But so this is q and this is p. So displacement is not capturing what's happening in these different places, it's capturing overall. This was delta r. So we want to know what's happening around this point or around this point, a particular point. So that means if I want to know around this point, I need to do delta t not that far, but very close. I need to q very close to p. So I need somewhere here and do average here. And keep doing it so that we take a limit, right? So there is an instantaneous velocity. That means as q kind of approaches p, at p is equal to average velocity, just like this, between p and some other point, say q, on the path as q approaches p. As you get make not so far in the future, you just get very close. You can even go from the past and you will get the same answer. So this means I need to take delta t goes to 0 limit in this all this average formulas. So what we're gonna get? We're gonna write v, which is same as we're looking at v at p. So these are all same things, okay? All same things. So this will be limit delta goes to 0, delta r over delta t. So we can all, that makes it some kind of derivative. So this will be dr dt. So this is like taking a derivative of a vector. And so if I go inside, so all of these become turned into derivatives. It's going to be dx dt, dy dt, dz dt. And of course this is a vector, so we should write, go this much along the I hat dx dt plus this much along this j hat direction and this much along the k hat direction. Okay, and because so suppose I went 2 I hat, I said 3 I hat, 4 j hat, for 5 k hat. So such a vector you can write, so I went 3 I hat this way, then I had 4 I had that way, and then so I went from here to there. So from this was beginning and this was the end. So this whole vector will be just this vector over here, right? Let me give a simple example. If I have a 3 I hat plus 4 j hat plus 0 k hat, so 1 2 3 1 2 3 4. So I went 3 I hat, and then I went along, I ended up over there, and I didn't go anything like that. So this vector is basically you're going from here to here. That's this vector 3 I hat. So this is 3 I hat for 4 j hat. So you can say how big is this? So this was 4 and this is 3, and you can also define what's the angle with respect to say x-axis is, call it theta. So this will be the magnitude. So magnitude will be square root of this square plus this square, 3 square plus 4 square, and that should just be equal to 5 in this case. And this angle theta will just arctangent this divided this, 4/3. So many of the problems will come not 3-dimensional, going to be 2-dimensional. So let's a little bit. So suppose I have a V. V is 3 I hat plus 4 j hat plus 0 k hat. Suppose I have this, and this is all meter per second. Its magnitude, if you look at, let me just make it so that we can understand. Its magnitude. So its magnitude will be kind of written like this, will be square root of 3 square plus 4 square plus 0 square. So in general will be square root of dx over dt square plus dy over dt square plus dz over dt square. Now I want you to look at what happened to instantaneous speed. See, instantaneous speed is just that thing, So instantaneous speed has the same formula as the magnitude in terms of velocity. So this is the same thing as ds over dt. Same thing as instantaneous speed. So this is velocity related concept. But if you look at just the magnitude of velocity is the same as the speed. So we say we may have a velocity as a vector, but its magnitude only instantaneous. So instantaneous velocity. So magnitude of instantaneous velocity vector is same as speed, instantaneous speed, not the average one. These are same quantity, okay? So there's another way to think about it. The direction does not exist for speed. But in the velocity, if we just look at it, this was 3 and 4, x and y, and so definitely this has direction, and I can use this angle theta for third here to say the direction of instantaneous velocity is this arc tangent 4/3, which is like a 53 degrees or something like that, with respect to positive x axis counterclockwise. That will be because I'm going from here, I'm going in that direction counterclockwise. I mean, that direction clearly is different from this direction. This if it was this direction, this will be clockwise. So the direction is contained in this angle, but it requires a little bit more specificity, specifying, etc. So this velocity. Okay, I think I'm going to postpone this discussion acceleration to another day because the video is already getting very long, and hopefully some of these concepts got clear to you if you are a little bit hazy on it. We are going to continue maybe tomorrow, another small video like that. Take care and bye.